Today we're happy to have Jize Yu back again from IAS to tell us about derived geometric Satake equivalence of Bezrukavnikov and Finkelberg.
Thank you for the introduction. Okay, so this is actually the last talk in the series of 4 talks towards understanding the derived geometric Satake equivalence of Bezrukavnikov and Finkelberg. So the goal today is to understand the following theorem. So there exists canonical equivalences of little triangulated categories so from this B G check per U H bar to this GO semi-direct products G equivalent direct category. So I will explain the notations later. And we have this equivalent complexes of C of G check.
Could you write a little bit larger because it's hard? The resolution maybe is not good enough. It's a little bit.
Sure, totally.
Louder.
Yeah.
Thank you.
All right, louder. Okay. So the geo-equivalent derived category of FMS finding. So here we have this box as a superscript of UH bar and this symmetric algebra of G check as to identify.
Excuse me. What's the argument in the DG check perf? I cannot read it.
You mean this one or?
I can't read it either. What is that? Inside the parentheses?
Oh yeah, that's UH bar. It's the quantized universal I'm-looking algebra of G check.
Of G check.
Of G check, yes. Right. So writing this box, basically, we think of this UH bar as a DJ algebra with a trivial differential. Okay. So this is to make UH bar and this same G check into DJ algebras with trivial differential. And we put H bar and elements in G check in degree 2. So this perf is perfect complexes. So those are the complexes generated by V tensor UH bar and V tensor symmetric algebra of G check. So V is a representation of the Monster group by taking direct sums and cons. Is the writing big enough? Okay, no abstraction. Any objection?
I'm just trying to set things up. Sorry, UH is the Riesz algebra of the enveloping algebra?
Exactly. This is the Riesz algebra. And I think this appears in Ann's talk, I think. Right, exactly. This is the Riesz algebra construction of the.
I mean, can I ask you, you're talking of complexes over the symmetric algebra. That you mean DG modules when you say complexes? Is that what you mean?
Right, DG modules, exactly. Yes.
Okay. Well, okay. Yeah, because before you said DG algebra, so you're really making DG modules, and so, yeah, okay. Perfect is the usual notion.
Right.
Okay.
Okay. So yeah. So let me just very briefly remind you why we care about this derived geometric Satake equivalence. So I think this is usually referred to as Drinfield's question. In the classical long-length program, we have a family of commuting operators, so-called these hyperoperators, acting on the space of automorphic forms. And the eigenvalues and eigenforms give us a lot of useful arithmetic information. And in the geometric long-length program, so the hyperoperators at a point can be thought of as the GO equivalent derived category on this Avant-Grassmannian. And Junfeld asked this question, how should we describe this equivalent derived category in terms of the long-length dual group of G? So I think the first answer towards understanding this question is established by looking at the heart of this triangulated category, that is the geometric Satake equivalence, which I described in the first talk. And I'll show you this picture. And later, I think Ginsburg considered this geo-constructible, this category of geo-constructible perverse shapes on this Avant-Grassmannian, and it has all these beautiful results which were discussed in Lin's talk. But here is a little bit of a drawback by thinking of geo-constructible. That is because this geo-constructible derived categories of shapes on Avant-Grassmannian does not process a monoidal structure. So we have to modify this Ginsburg's picture by really looking at the geo-equivalent derived category of Avant-Grassmannian. And this is the modified Ginsburg's picture, and this picture is described by Lin and An's talk. Okay. So we also mentioned that despite that we have a bunch of results towards understanding this geo-equivalent derived category, this is still very hard to get an understanding of this category by the long-length dual group of G. So what Bezrukavnikov and Finkelberg did was actually they add in an extra parameter, that is the loop rotation by GM. So by adding this GM loop rotation, we look at this GO semi-direct product with GM equivalent derived category of shapes on the Avant-Grassmannian. And this blue column is kind of like the topological world in the paper of Bezrukavnikov and Finkelberg. Well, these red letters are the algebraic information in Bezrukavnikov and Finkelberg's paper. So, so today I will spend most of the so today the first half of my talk will be focusing on describing a filtration of this equivalent hypercohomology functor on the topological side, and I will also describe an algebraic filtration and a constant functor on the algebraic side. And in the second half of the talk, I plan to compare these two functors by comparing their corresponding associated gradient, and eventually we get a link, which is a full embedding from this freely generated Harishchandra bimodules to this geo semi-direct product of the GM equivalent derived category, which extends the Satake equivalence. And finally, the comparison of the topological filtration and algebraic filtration will allow us to prove the main theorem as stated in the goal. Okay.
Sure. The kind of never mind.
So let's look at the topological filtration.
No, I did have a question. So when you were defining these DG modules of the form V tensor UH or V tensor sim,
Yeah.
what's the grading on V?
What's the grading? Grading on V is just the put on degree 0.
It's all put in degree 0.
Yes.
And so the action of, there's no action of UH or sim on that, on. So they're acting fairly freely via the multiplicity space, but then you're encoding that to the action of G check that you're taking equivariance.
Right.
Understood. So you didn't need that. When you're defining, if you didn't have the G check equivariance, then your definition of perfect complex is you don't need the V because it's just a multiplicity space.
Right.
Okay.
So so we will first discuss the topological filtration of GO semi-direct product with GM equivalent. Okay. So first of all, we know this T cross GM equivalent homology of the perverse sheet. So whereas it's just the geometry Satake equivalence. So this is isomorphic to H of GO semi-direct product with GM equivalent homology of the same sheet, but we need to tensor over O of T cosine W plus A1 with O of and this is in fact isomorphic to pi identity R of the O semi-direct product of GM equivalent homology. So here this pi identity. This is from T cross T cosine W plus A1 to T cosine W plus T cosine W plus A1. So recall, I think in N's talk we proved that this GO semi-direct product of the GM equivalent homology functor actually gives us T cosine W squared cross A1 microstructure. And in fact, this is a deformation to a normal cone. Anyway, this we can refer to in N's talk. And now we will install infiltration.
Sorry.
Yes.
You're just using the induction of circuit.
You mean here? You mean this isomorphism? I'm basically I'm using the equivalent homology.
Yeah. Okay. Sorry, I was trying to parse.
Right. Yeah. They're definitely correct. So we can install infiltration on this T cross GM equivalent homology of this sheet S of B. So because the actual definition of this filtration is actually kind of technically involved, I will not give a very precise description of this filtration, but rather I will say this is like the equivalent version of the Merklich-Vallone filtration. To be a little bit more precise, I'm really looking at the T cross GM equivalence version of the weight functor defined by Merklich-Vallone. So recall here, this T lambda is the n minus I orbit of this T stable point T lambda, where this T lambda is the image corresponds to this co-character lambda. Okay. So although the description of this filtration is a little bit complicated, but its associated gradient is not hard to describe. So for any representation of the Lambda steel group G check, the associated. Okay, so the above filtration as associated graded equals to direct sum of identity by identity over O of a gamma lambda and the tensor with V of lambda. So here, what is this gamma lambda? Gamma lambda is the set of triples x1, x2, and A, which belongs to T cross T cross A1, satisfies the defined by the equation x2 equals to x1 plus lambda A. And V lambda, this is just a lambda wave space of the representation B. And moreover, the filtration of this as weighting. So very interestingly, this filtration actually is compatible with the monoidal structure of this equivalent hypercohomology function. I want to make this quick. Yes, and is there any question?
Am I supposed to think about this O as some kind of standard binomial? What am I thinking about this as?
You can think of it as
for Ben, this is exactly a standard module in this context.
Right.
This is exactly a standard bimodule.
Associated to the element of the wild group, which is translation by lambda.
Exactly.
Okay.
Yeah, or you can also think of it as the T times GM covariant homology of a point. So this is from topological perspective.
This is splitting as what?
Splitting as right. This is splitting as O of T percent W cross A1 module.
As a binomial.
Right, bimodule, yes.
Okay, but binomial. You're doing a push forward, so you're doing a module on one side.
Right.
It's a bimodule over two different.
Okay, what is it? It's a module over what?
This is module over.
Why not just let R be OT? And never mind.
So this is module over just OT.
Okay, a module, not a bimodule.
When I speak about the splittings, as
Okay, so it is a bimodule, but it has a splitting only as a module.
only as module.
Okay.
So let me very briefly remind you, this here is our modular structure of this equivalent hypercohomology function. So we have a isomorphism, which I give it a name top.
I'm sorry, in this filtration, so these are filtrations of graded bimodule. And the associated graded is a graded bimodule. And V lambda is graded in degree 0 or with?
In degree 0.
In degree 0, okay.
So we have this isomorphism from from this GO, G as E1 2 equivalent cohomology of SFE1 and the tensor over O T pushing W plus A1 and with GO semi-direct products GM star Okay. So roughly speaking, lemma 1 implies that we have an isomorphism O TM star of S of the tensor O to W to state 1. This is isomorphic too. O became a lambda tensor A T plus A1. And we tensor the entire thing with the wave space B of lambda. Okay.
Oh, sorry. B of lambda is the weight space of B.
It's a wave space, lambda wave space of B.
Sorry. Okay, I understand.
Yes. But this comes to, right, as you mentioned, this is really by applying the Merklich-Millon and weight factor to the shape as B. Yeah.
This K is a fraction field. What is K? T times A1.
What is K? K, right, this is the fraction field.
You take the board you just wrote on it and slide it up.
Okay, you can't. It's in the back.
Oh, okay.
Oh, you can't.
No, I can't.
Oh.
This is fixed here.
Okay.
So the proposition basically tells us that so this filtration is compatible with the modular structure of this equivariant hypercohomology functor. So that is to say, I'm going to draw this picture. O R above with O. And here we have this topological monoidal structure.
What is a star?
What is this convolution? This convolution, right, I forgot to say, this convolution is defined to be this equivalent homology tensor with each other over O T quotient W plus A1. This is a definition of the convolution of the yeah. All right, we have this homological monoidal structure, and this gives us the GO semi-direct product with PM equivalent homology of S of V1 tensor V2, and we need to tensor with and here we have this in V1 above with half. And this basically gives us direct sum of lambda, well, O gamma lambda tensor O of T with W plus A1, K of T plus A1. And we tensor with V of lambda, and we answer this with everything. Just basically you just
V1 of lambda.
yeah. So exactly V1 of lambda, and let me just be a little bit fluffy. It's something, and consider with V2 lambda prime. Okay. And at the bottom, we have this top of V1 tensor V2, and this is lambda again with T1, and I tensor was lambda with space of even tensor V2. And this is not hard to check this isomorphism under this diagram. So this is basically by what I say this filtration is compatible with the modular structure of the equivalent hyperpolarized functor. Okay.
So would this not be true if you hadn't passed to the fraction field? Because you still have the arrows, right?
Let me see.
Well, it's certainly not an isomorphism of the direct.
It's not right. It's not an isomorphism.
Wait, sorry, which one? Which one is not an isomorphism?
He's using this isomorphism. He's saying the filtration splits after you pass the fraction field. So that after you censor the fraction field, it's a direct sum of all these pieces.
Wasn't the statement that it splits before passing it?
No, it does not. It splits as a left module, not as a bind module. As a left module, everything's trivial. O gamma lambda is just a free module of rank 1 as a left module. Like this is nothing interesting.
Mm-hmm.
I mean, this maps if you don't enter the fraction field, right? Yes, sir.
Not to the direct sum of the associated graded.
Wait, you mean from left to right? Are you from left to right?
Yeah, or in either direction. Yeah, we're talking about left, right, not up, down. Up, down surely exists.
Sure.
No, I thought the statement wasn't. You wrote down that it was mapped right before without the fraction field. It was like a proposition, and then there was like a corollary
Right,
retention of the fraction field. So there was definitely a map before.
I think the proposition was that the associated graded is this, and then the corollary, and then was that of the splitting was that you pass to the fraction field isomorphic to a direct sum.
It's not my memory, but we can revisit at the break or something. Maybe.
Yeah. Okay, I think it's already 3:30. Should we have a break?
Yes, let's have a break.
Okay.
Can I ask a general question?
Sure.
So I'm looking at the right part of the diagram on the top board. And I definitely know something about one of these functors, which is, I think, denoted by KH bar and is constant functor.
Right, this is a constant functor, yes.
So, well, I'm not sure what is HC tilde is, but I assume it's ambient abelian category.
Oh,
is it ambient derived category?
This is the category of asymptotic Harshchandra bimodules.
Yes, but is it abelian category, derived category?
Right now, you're on a derived.
Right. Right now, this is derived.
This is the derived. Right?
Derived word. Yes.
There should have been some derived earlier too, presumably.
Okay. In any case, so I know that the constant functor is a quotient functor, and I know what it kills.
Right.
And I know that it's fully faithful on certain objects and so on. Well, I mean, it's fully faithful on a certain subcategory of the abelian category. It's not fully faithful in derived category. But in any case,
I don't think HCH bar tilde is the derived category.
It's abelian.
Yeah, and I think so the difference between H bar and HCH bar tilde is just that we don't require the finitely generate. So for HCH bar tilde, we don't need finitely generated.
Okay, in any case, so I think that also the quotient function, if you drop the condition of being finitely generated.
Right.
But now, question number one, do we know this about the bottom vertical arrow?
So which vector?
Well, I mean this H star gr.
You mean
G or whatever it is.
You mean this vertical functor?
Yes.
Yeah, sure.
So I mean, so one way of proving that we have, well, and I assume this S sub H bar is going to be an equivalence, or what? Or is going to produce an equivalence. So my question is, so suppose that we want to prove an equivalence of category HC3 with some category which has to do with derived category of Fine-Grassmannian.
Right.
So can we just say that, you know, both of them admit a quotient functor to the same category, and these quotient functors have similar properties, and they're sufficiently nice so that their existence will yield an equivalence. So think about, I think there is an analogy of this story with Sorgel's story, where, you know, you have projective modules in category O, which are just then equivalent to something like semi-simple complexes of pairwise shapes, and then you have two quotient functors, which are of very similar nature to what we have here. So it's another observation. So can we just use some property of the category on the left-hand side, this derived category of Fine-Grassmannian, to get
the derived equivalence?
Well, I mean, it's not going to be a derived equivalence because on the left you have some additive category, which is HC3. But maybe we have some, you know, nice additive subcategory in this derived category on the left-hand side, and we can get a category equivalence for some, you know, reasons. Does this question make sense?
Yes, I think this is right. I think this is actually related to the proof of the derived equivalence. Actually, if you look at this subcategory of the equivalent derived category, which is generated by semi-simple objects, and we know that this hypercohomology functor restricts to this full subcategory is fully faithful. Well, the constant functor is also restricts to this HC H bar free. It's also a full embedding, and this produces us with a functor such that it sort of maps the generators on the left-hand side to the generators on the right-hand side, and the home space, it maps the home spaces to the home spaces via isomorphism, and this is actually used in the eventual construction of the derived equivalence.
So can I ask? Is maybe even are you maybe asking about having something stronger than just fully faithful, something like one faithfulness, or are you asking about possible property like that?
I doubt that the constant functor is one faithful.
Yeah.
Even after even after deformation.
I mean, I think the Sorgel, this is parallel to classical Sorgel story.
Yeah.
Where you don't have a one faithful functor.
You don't need it.
But it could be better. No, it can't be better. You think after deformation?
Well, I don't think there is anywhere to deform. Although maybe I need to think about it some more. But I mean, Raphael, so this constant functor is, is deformed functor V in essence, right? So, but then,
so that's what it's already deformed. That's what I mean. I mean, it's like circle deformed. It's not the analog of circle. It's analog of a deformed circle here, isn't it?
But it's circle deformed and homogenized. So I'm a little bit worried about. I mean, it's let me put it this way: this functor has some potential to be one-faithful for the reasons that the codimension of the principal locus in G, codimension of the complement is big or equal than 3.
Even two-faithful, maybe.
No, I mean it's going to be one-faithful. But one needs to be a bit careful with making this statement.
We should probably continue, right?
Yes, I think so.
Correct. Okay. Okay, so let's look at this algebraic filtration on constant functor. So first of all, we introduce a slightly new functor which we call just kappa h bar. Pi will be t check star to t check star to w, and we define this universal Verma module, which we notify m h bar and sub rho to be u h bar tensor with u h bar of h hat and so here rho is the half sum of the positive roots, and this u h bar b check module structure of this k of t check h bar. This rho factors through this u h bar of t check. So where t x on x equals to tx minus h bar rho t of x. Okay. So now we can define this functor h bar of m where this right. So where this m is an asymptotic Hartree-Schindler pi module. This is defined to be m h bar, and it's pro tensor u h bar with m is u h bar. And check minus the second copy is this side. So we have seen this part in the definition of a constant functor, and this is asymptotic to. I should be right over there. Sorry. This is to chat r minus rho. Tensor u bar p chat is m. Okay, so first of all, we observe that the center of UH bar embeds into a second copy of UH bar, UH bar over H bar. This thing maps, this thing acts on this kappa H bar. And so in this way, we really get T quotient W cross A1 structure. And on the other hand, we know that U H bar of T check also acts on this kappa H bar. So this gives us O of T cross A1 module structure. So
sorry, I need you to slow down for a sec because I'm still trying to figure out what's going on a couple of bits before. So chi sub h of m. M is
some asymptotic.
Have we defined that yet?
I think we mentioned this in Ann's talk.
Could you remind me what it means?
Sure. This is basically okay. So this is basically UH bar tensor UH bar by modules, such that can't remember this. Maybe like or this things.
Sorry, UH bar of what? Of T?
Over KH bar.
Of T or which?
Oh, of G.
Okay.
Entirely algebra.
Okay.
Such that let's see, plus 1 tensor x, like some m. This is probably I think it's yeah, it's better.
Just want them to be ad integrable.
Sorry, pardon me?
Like, it's just, I think it's enough just to say that they're ad integrable for the adjoint action.
Right.
Okay, got it. Right.
Where you need to divide that joint action by h bar.
Right.
Because you're right.
Okay.
Yes.
And so this is a bimodule, and so you're tensoring it up. You're taking this negative row from a module, tensoring it on one side with m, and then what's the second thing that you're doing?
Right. This is UH bar of
Is that n?
This is unchecked because yeah. So K of H bar. So such that is psi alpha equals to 1 for every alpha is a positive, right?
Okay.
You mean simple root?
So simple root, yeah, because you're killing two.
Oh, right, simple, yeah, synchronous, yes, of course. Thank you.
All right, and then you're tensoring over UH of n minus on one side. Sorry, the two is it subscript?
Okay. So okay, in the definition of this constant functor in the paper of Bezrukavnikov and Finkelberg, they actually expand this from a single copy of UH bar of n check star to like 2 copies of the tensor product of these two. And here, this 2 means that we're using the second copy of this action on this side. So.
But so when you're tensoring with psi, you're viewing psi as a module over UH minus. So when you're done, when all is said and done, what you have is as a module over what? It's got UH on one side and just on one side. That's it.
Pardon? What is on one side?
What module structure remains when you're done with this?
When I'm done with this, right. This is
one thing you explained with the center is talking about the central action, center of UH.
Right. So after tensoring all this, so we get like 2 actions. One of them is the center of this UH bar, and the other thing is this UH bar of T check. So to combine this action, these 2 actions, we actually get like T times T quotient W cross A1 module structure of this chi H bar of M. So this is the module structure we will use in the later construction.
So should I understand that, before when we talked about constants functor, we took n invariants, but now we somehow take n co-invariants, but we do it in a derived way, so that there is little difference.
Right, this is a little different, but later we will see that this functor chi h bar is not really that different from the cosine functor. It's almost the same. I will say this in a second.
I'm not sure if this is correct, but I think one way to think about this is that on the topological side, we went from G to T.
Right.
And we're trying to work out an algebraic way of going from G to T.
Right, exactly. Right.
Well, I mean, it's, I think it's more like going from T mod W to T.
Yeah, that's exactly the same thing in equivariant cohomology.
Yeah, okay.
Yeah. Let's see.
So the reason we care about this new functor is now it's not really different from cosine functor. This is as a more than 2. So we call this is the cosine functor. And there's another lemma saying that so there is there's an O T
Sorry, again, V is just a straight up multiplicity space, or is this my fancy again?
Still the multiplicity space. The version okay, let's just say. So there is a equation on this 5b.
What's 5b?
What's 5b? 5c is right here.
No. Sorry, var 5. That's var.
Oh, var. Sorry, var 5b.
So what's 5b?
5b is the cosine functor applies to this UH bar tensor B.
The cosine functor?
That's the cosine functor restricted to HC. Right. So this is HC H bar, not that bar. That is to say, the object security comes from representation of G type.
Yes. And then what's the cosine functor?
You mean this one?
Yeah.
So this cosine functor is equal to the normal form of P equals W squared plus A1. Such that we map module M to and reverse second copy of some side and take the n check minus equivariant part of it.
What about the claim that V is simplicity here, though? I thought that the T mod W action was like the G action.
Right, this is this T check star which in W is kind of like twice around G. Okay, I think we can discuss it later. And right, so there's a filtration on this for 5B with associated gradient. So this takes a very similar form as the topological filtration. And moreover, it is compatible with the structure of the cosine functor.
So when we just like just to clarify, are we in the DG setting or are we actually talking about modules?
We're actually talking about modules. Okay. So next thing is speed up a little bit, but this one basically topology versus algebra. So this theorem tells us that for any representation B of G check, so there is this unique isomorphism of O T quotient W cross T quotient W cross A1 modules which we denote by eta of V. This comes from the equivalent homology of sheaf on the Frank-Grossmanian to this functor like we described before. And moreover, this eta of V is compatible with the monadal structure of the hypercohomology functor as well as the cosine functor. And this topology equals algebra type of result allows us to prove the following theorem. So, so this Satake equivalence to this TO, semi-direct equivalence to TM, therefore G functor G. So this extends uniquely to and here this is E O. That's uniquely. This is actually the functor as H bar. I drew in this diagram, and from here we have this cosine functor H bar, and here we have this equivalent homology functor. And it all lands in the geo equivalent potential sheaves on deformation to the normal cone. And this is unity. Finally, I will very briefly talk about proof of the theorem. The idea of the proof is, so we hope to find, or we hope to construct a functor that's actually bar glass GO semiconductor GN equivalent to sheaf under G. So such that this when we restrict to HC of H bar bar, and this functor equals to the thing we get. So let's say we can do this. Then we notice by the property of this SH bar, we know you send generators to generators, and also this is the full embedding. That is to say, it takes home spaces as markedly to the home spaces in the target category. Then this is then by Balance's lemma, we know that this functor here really induces an equivalence of categories. And how exactly this functor is constructed, this is we basically hope to pass through and we really hope to construct a family of functors. So lambda, this is from D to of UH bar box, then equal to lambda to the GO semiconductor product is GN, is equal to lambda. So here, so this category basically means, interesting. This is basically a full subcategory. So this is the full subcategory of the check curve of UH bar box. Say, such that so this is generated by objects of the form UH bar and V, where this V is representation of G check of pi squared less than or equal to lambda. Right. Let's say we have constructed a family of functors from this full subcategory of this G check equivalent perfect complexes to this equivalent derived category of this Schubert variety, such that it's compatible. For example, if lambda is less than or equal to lambda prime, the lambda prime restrict further to this lambda level is as marked to this functor constructed at lambda level, and we are done. And the construction of this functor is basically a formality argument which involves the purity of the IC sheets of functors meant. So this is pretty technically involved, and I don't think I will have time to talk about it. Okay, I think this ends my talk, and thank you for your attention.
Any questions for Jize?
So I'm looking at this theorem here. So how much do you lose when you kill H bar?
How much do I lose if I kill H bar?
So I mean, so when you kill H bar, you're going straight to Zirkel, singular Zirkel binomial, and do you sort of lose the ability to discuss what the filtration means? Or what do you lose?
Actually, if we let's say if we lose H bar, and this corresponds to taking the zero fiber on the topological side, and this actually recovers the GO equivalent derived category, the result on the GO equivalent derived category.
That's actually not what I wanted then.
Ben, can I just make a comment?
Yes.
So if you have H bar, that's like requiring your representation of the affine Weyl group to be faithful.
Okay. Yeah.
And killing H bar is saying it should factor over the finite Weyl group.
So wait, H bar? No, really? That's what
yes.
H bar? That's the role H bar is playing?
it's like I don't know what we would call delta.
It's delta. Oh, but okay, but I thought that you were getting modules over like an indulgent algebra rather than just a sim. But I guess when you're looking at the torus, it's the same, and so there's no problem. Okay. I thought there was some non-commutativity going on in what you were getting a module over, but in the end, you're getting. No, I'm being stupid. You're getting coherent G's on something, so it's modules over commutative. Okay. So sorry, this deformed normal, this normal deformation to the normal cone thing. What is the global sections of that again? Remind me.
The global section. It's the it's just a how should I say? It's sync. So the global section should just be so O of x together with this f, such that f restricts to diagonal equals to 0. So it's generated by functions of this form.
Yeah, but I don't remember.
Sorry, I mean probably that I can which part numbers.
You should just assume that I don't remember what happened to the previous talk. So.
Okay. Right.
Jize, can you leave that? I think it's really important to have that still on the board. So
yes,
would you mind rubbing out something else? Because I think further discussions would probably focus on that.
Right. So let's say we have a something. Deformation for normal cone is something over A1. So the picture is really like, so okay, this is a copy of A1. So if it's fiber away from 0, it really looks like a copy of Y. I don't know how to draw it, it's really like Y. And the fiber at 0 is a normal cone. Maybe I should see Y. This is really like a normal cone of it. So this is basically apply a risk construction. That is, if you really like look at it, 0 fiber is the associated gradient, and the genetic fiber is just a copy of Y. So that's the deformation to a normal cone. And I think
the genetic fiber is a copy of Z. Z is the bigger one, right?
Yeah, sorry. Yeah, you're definitely right. That is the bigger one. Yes. Thank you for pointing this out. Yes. So in the language of algebra, this basically means that if you take the generic fiber, it's just we forget about filtration. So
I see.
Right. I should complete.
But OT is, polynomial, full polynomial is in there somewhere.
Okay, let me just finish this. Here, I have this.
Okay. I'm a lot happier now.
Great.
And just to like Ben before asked, can you see this filtration with H bar turned off? And you'll notice that all of these graphs become just the graph of the identity when H bar is turned off.
Right. Is that right? Yes.
So at the end, when you say you finish off using a formality argument, you mean like you just say where the object goes and you say like where the boundary spaces go? Like,
I'm just right. I just consider what is the what is this anamorphism space of the sort of the generators in this truncated Harshchandra, freely generated H-bar Harshchandra bimodules, and this is isomorphic to this direct sum of this anamorphism of this direct sum of this IC shifts on the Schubert variety. So, and this is isomorphism, and right. This is basically the formality argument we use to construct this functor.
To say that a map anamorphism is enough to specify a map on like derived anamorphism. That's what you're saying?
Right. This is actually by this more general result, the proposition 6 in the paper.
Okay, but you're saying that's the content of formality.
Tony, the content of formality is the fact that the DG algebra of endomorphisms of the direct sum of the IC sheaves on the affine Grassmannian is formal.
Yeah.
So there's a question from Jody about the monoidality of this theorem at the end.
Yeah, I just wasn't sure. So just to rephrase my question more precisely. So I understand that at various points, so we have this equivalence, the Satake at the top, and then we have this functor SH bar.
Right.
And I've understood that at certain points, we've shown that the two arrows to this coherent world below are fully faithful.
Right.
And I wanted to know what was the exact content of the theorem. Is it the fact that this is all monoidal now?
You mean which theorem are you referring to? Because so this cosine functor restrict to this subcategory is already fully faithful, I think. And
is it monoidal?
This one is monoidal. This one is monoidal. So I should say we should really think. So what we really use is this one to be kappa H bar and U H bar. And for this functor, we have a monoidal structure. So so we really think of and the comparison of the monoidal structure on the topological side with the monoidal structure on the topological side with the algebraic side is really the comparison of this one and with this one instead of with kappa bar.
I see.
So ultimately, you think it is monoidal.
It's a monoidal.
And if you forget the GM action, at least it's actually braided monoidal, like on one side and symmetrical monoidal on the other side. So is the equivalence braided monoidal?
So I don't quite.
There's a braiding, symmetric braiding on rep G check.
Yeah, but I think for the derived thing, forget the GM. Forget the GM equivariance.
Right.
Then the equivariant derived category will be braided monoidal, like more than monoidal, and then the other one will be symmetric monoidal. And I'm wondering, like, if you know that if it equivalent is also compatible with braided monoidal structure.
Can I? If we're going to ask that question, can I first ask where the braiding comes from geometrically?
Oh, yeah, it comes from like fusion.
Right, but I was hoping for a nicer answer.
I'm not sure. Braiding comes from fusion, so it's hard to understand, I think. So for this question, I don't know the answer.
I mean, I've been wondering this question for quite a while. Does anyone have a nice description on the level of coherent sheaves down at the bottom of how that braiding should come, the geometric braiding should come. I would love to know the answer to this question.
If the equivalence is braided monoidal, then that would be even answer.
Yeah, but that's not the answer I want, right? I don't want to say, oh, we'll just transfer it from the other side. I mean, if geometric Satake is supposed to mean something in the braided sense, it should be matching two things. And if there's this third version of it, then there should be something there too. I understand there is a symmetric braided structure you can put there. So to give you some context for my question, Rep G-check has a Q deformation for representations of the quantum group. And coherent sheaves, GM coherent sheaves has a Q deformation. Whereas as far as we know, perverse sheaves does not have a Q deformation, or no one's defined it. And so I would like to know how to define the non-symmetric monoidal braiding on the geometric side on the bottom, on the coherent sheaves geometric side, in order to match things up. That's what I asked.
And why do you say that the coherent sheaves have a Q deformation?
Because that's my quantum, my favorite Q deformed Cartan matrix.
Mm-hmm.
Although things might be different since H bar, there is no H bar in this. Ah, there is no H bar. That's interesting. Okay. H bar isn't central, I should say.
So I think Ivan has left, but did anyone understand what he was saying earlier with the intuition about like one faithfulness and like this? So I understand roughly an analogy between this constant functor and the Zorgel functor, but he says this is not just deformed but also what, analogous to a deformed what Zorgel functor.
Some context you might want to have in mind, Mackie, is that
yeah.
So the Zorgel functor is like Hom from one projective.
Yeah, no, I understand it's killing stuff, so it's
it kills almost everything. But what if you take Hom not just from the minimal projective, but also from the subminimal projectives? So the direct sum of the minimal and the subminimal.
Mm-hmm.
So this still kills a lot of stuff.
Mm-hmm.
But you know the problem that happens before for the Zorgel functor is that all the Verma modules go to the same one-dimensional module.
Mm-hmm.
And so in some sense, you're sort of messing up Hom spaces between Vermas.
Mm-hmm. Yes.
But if you also throw in these subminimal projectives, then you actually preserve the structure of Hom spaces between Vermas too.
Mm-hmm.
So this is related to the definition, to the notion of one faithfulness, which I can't actually reproduce for you right now.
Mm.
And you get one faithfulness if you sort of soup up the Zorgel functor in that way.
Mm-hmm.
But they were suggesting that maybe you get one faithfulness in this setting also.
Mm-hmm.
I just, you know, I have no idea if it's true.
I think one faithfulness maybe is the fact that x1s between Verma are the same as the x1 of the images of the Vermas. Is that what it is? I forget. Something like that.
I think that's right.
Mm.
So you basically the Verma filtered category is the same as its image.
Yes, I see.
Yes.
And did anybody understand what Vanya? So Vanya wrote that he apologized he had to go to a committee meeting. I mean, he'd much prefer to be here. But did anybody understand what he was saying? Like, what's the baby example of this in Zorgel land, where you have two quotient functors and?
Well, I mean, he was just referring to Zirkel's isomorphism between category O and perverse sheaves, like the semi-simples and the projectives and the two different sides each go to Zirkel bimodules. And so you can.
But I kind of felt like he was saying something a little bit, because I can see,
he was,
okay, I have two.
He was asking, yeah, he was asking for more. He was asking if there was a unique, nice kind of highest weight category with a quotient functor. So if you have two nice highest weight categories with this quotient functor to some sort of circle bimodules, I mean, are those categories automatically equivalent if you know a little more? That's what he was asking, I think.
Right. So, I mean, Ivan has lots of theorems along these lines if you have one faithfulness.
But is that something that's ever been used in things related to circle bimodules? Or, I mean, what you're saying is that so that's something you use, isn't it? That's what you were just explaining. Is that the only case, or?
That's the only case I know about. But I mean, Ivan was already using this stuff for proving uniqueness of tensor product categorifications.
Yes, it's been used in many settings. Yeah, many settings like Cherenik algebras or more this setting. But here the difference is that you land into a fairly world more like modules of I mean, having to do with commutative algebra. So that's a weirder world to land in.